So, hello, my all dear students. I welcome you all in this video. In this video, we will see the unit 2 of our subject, that is the power electronics converters for renewable energy. So, this unit is basically dedicated to DC-DC converters. So, as its name suggests, the DC-DC converter means input is DC and output is DC. So, what is the difference basically? This is the fixed DC and this is variable DC. So in this way, let us say this is the input voltage Vi and this is the output voltage V naught. So there are some possibilities. The possibility number one is Vi is greater than V naught. The second possibility is Vi is less than V naught, and the third possibility is both greater than or less than equal to V naught. So based on these three relationship, there are three types of DC-DC converters which we have. So the buck converter, boost converter, and the buck boost converter. So this is the buck converter, this is the boost converter, and this is the buck boost converter. So all these are the DC-DC converters, and the buck converter is also known as, since the output voltage is less as compared to the input voltage. So this is the step down. We can say this is the step down chopper. The DC-DC converter, DC-DC converter is otherwise known as chopper. Okay, so this is the step down chopper. This is the second one is the step up chopper. This is the step up chopper, and the third converter is known as the, which is the buck boost. It is known as the step up step down chopper. Step up step down chopper. So in this video, we will see the very first chopper, that is the step down chopper. So let's say this is a fixed DC. This is a fixed DC voltage. Let's say this voltage is VDC, and now this is the load across which some output voltage has to appear, and that voltage is V naught. So if I connect directly this VDC across this V naught, so same VDC I will get here. So there are two ways to regulate this output voltage. The way number one, which is the very conventional method, it is the potential divider method. So in this, by changing the value of this resistance, I can regulate this output voltage. But what is the drawback? That I have to compromise with the voltage drop across this R. So this is not usually preferred. So what is the very popular way to regulate the output voltage? By using this switch. This is not the ordinary switch. This is the fast operating switch. This switch is fast operating switch, and this switch is known as chopper switch, and most of the time we are using the MOSFET here. Okay, so this switch offers the high switching frequency. The switching frequency is very high, means it's on and off time. The on and off time of this chopper is within the few seconds it can on, within the few seconds it can off. So now, since now it is the switch we are having, so what is the relationship between the output voltage and input voltage? Now this relationship based on the switching cycle. This relationship is based on the switching cycle. So what is switching cycle? Switching cycle is basically what is the on period and what is the off period. What is the on period and what is the off period? So let's say from 0 to t on, the switch is on, and from t on to this capital T duration, the switch is off. Means this duration is t off, and capital T, which is the time period, it is equal to T on plus T off. And what is the frequency? So frequency is 1 upon this capital T. So this is the switching frequency basically. So with respect to time, this is the duty cycle. So now the on time with respect to total time is the duty cycle. The on time with respect to total time is that duty cycle. So this is represented by alpha, and this alpha plays very important role in regulating the output voltage. So the output voltage is related to input voltage by for how long the switch is on over the complete time period, and the output voltage is the this duty cycle with the input voltage. So we can say this is the average value of output voltage, and it is the alpha times of Vi. So now This is the average value of output voltage. This is the average value of output voltage, and we can see this alpha can never be greater than 1 because our T on is always less than capital T. So this alpha is always less than 1. Means in this case, we always get the output voltage less than the input voltage. That's why if we connect a simple chopper switch in series with the input voltage, we can realize this circuit as the buck converter. We can say this is the step down chopper, or we can say this is the buck converter. This is very simple to realize, and this value which we have derived, this is the average value of output voltage. And if someone asks what is the RMS value of the output voltage, so RMS value you can find it is the root of alpha times of input voltage. Okay, now let us see what is the resistance introduced in the input circuit of the chopper. So this is basically Vi upon Ii, and this Ii is equal to I naught because our circuit is series circuit. So whatever the current is introduced from this source, the same current is flowing to the I naught, and I naught is basically V naught upon I naught is basically V naught upon R naught. Let's say R naught is the load resistance, so we can say this is the V naught upon R naught. Now I can write this II as now V naught in terms of Vi. So this is V naught in terms of Vi. We can write alpha times of Vi. So this is alpha times of Vi divided by R naught. So this R naught is equal to alpha times of Vi upon II, alpha times of Vi upon II, and we can say this R naught again is the alpha times of Ri, since Vi upon Ii is Ri. So the input resistance is basically load resistance divided by alpha. So this is the another relationship what we have. Now we will see some performance parameters. There are two performance parameters basically. The one is the voltage ripple factor, and the another one is the form factor. So the form factor, by definition, we know the form factor is the RMS value upon average value, and the RMS value is alpha root alpha times of V naught, and the average value is alpha times of V naught. So this is the form factor. This is the form factor of the buck converter, and the voltage ripple factor is the another performance parameter. So and it is equal to the form factor square minus 1. So this is the basically formula. This is the formula for voltage ripple factor. So it is the voltage ripple factor is equal to under root of form factor square minus 1, and the form factor is equal to V naught RMS upon V naught average. So we can, if we are having the value of alpha, we can comment on the form factor and the voltage ripple factor. Now two control strategies we are using in this converter. The control strategy is, the first control strategy is the time ratio control, and the second control strategy is the current limit control. So what we do in the time ratio control? So time ratio control basically, there are further two types. The one is the constant frequency control, and second one is the variable frequency control. In case of constant frequency control, we make this capital T constant if we are changing the T on. So for making this T constant, we have to make the appropriate change in T off also. So if we are using this strategy for controlling the duty cycle of chopper, then this is the time ratio control, and this is the constant frequency control, and second one is the variable frequency control. It means if we are changing the T on, so do not change the T off. So in this way we are varying this capital T. So that's why this scheme is known as the variable frequency control. And the second control method strategy is the current limit control. And in the current limit control, in this case, the duty cycle of chopper is guided by the minimum and maximum value of the load current. So this is again the second control strategy, which is very important: the time ratio control and the current limit control. So thank you for watching this video, and in the next video we will discuss the boost converter. Thank you.